Hey, well, now I can pause the recording, so okay. It must be working. Okay. Wait, participants. Ned, I'm going to make you co-host so you can let people into the. There are still some people coming into the waiting room every now and then, so if you can let them in, that would be fine. Okay. Welcome everyone to the to my second lecture in the set theory course. Today's topic will be ultrafilters for one, and stationary sets for the other. These will be things that we will need when we talk about large cardinals later on. They're also used to, shall we say, motivate some of the definitions in the large cardinal universe. Filters, ultrafilters are also quite important in topology and logic. I actually have a quote that I should try and put here. I'll stick it in here somewhere. This is from the book The Theory of Ultrafilters by Comfort and Negropontes, which is a very useful thing to have if you're into this kind of thing. An ultrafilter is a truth value assignment to the family of subsets of a set. We will see in a moment what that means. And a method of convergence to infinity. It's being used in topology as a way to add points to topological spaces, for example. And ultrafilters also feature in model theory, where you take ultra products. You can prove the compactness theorem for logic using ultrafilters, and you can do various other things with them. This quote by, I guess Comfort wrote this. He was a man who knew his languages, and he wrote beautifully every now and then. And this tells you, if you know a little bit more, why filters and ultrafilters are important. But let's start with the definition. So what is a filter? We're going to be needing ordinary filters as well, and ultrafilters will appear automatically. And what does a filter do for us? Well, for one thing, the whole set should be a member. The empty set should not be. I know there are books that even let the full power set of X be a filter, but I'm not one of those people. So by stating that the empty set should not be in the filter, I'll leave that one out. If A and B belong to F, then the intersection belongs to F. Okay, fair enough. And if A belongs to F and B is a superset of A, then B belongs to F. This is the definition of filter. Ultrafilter will appear in a moment. Because I tend to forget myself, there is also a dual notion of ideal, and every now and then it's easier to talk about an ideal than it is to talk about a filter. So I will at least give you the definition of ideal on a set, and it's completely dual. So X should belong to the filter. What should belong to the ideal? Well, the empty set should belong to the should be in the ideal, and the whole set should not be. What's dual to intersection? Well, union. And what is dual to the third property? Well, if something is in the ideal and something else is a subset, then that should belong to the ideal. And by the way, this is an ideal for those who have done their algebra and ring theory. This is an ideal in the ring, what? The power set of X. The addition is symmetric difference, and the multiplication is intersection. If you interpret plus and times in this way, you get a ring. In rings, you have ideals in the algebraic sense, and that's the same thing as what we have over here. And an easy exercise, more an observation. If F is a filter, then if you have a filter, you can create an ideal by looking at the complements of your members. And if you have an ideal, you can create a filter by looking at the complements of your members. So what are some examples of filters? Well, there's always the sort of trivial example. I usually give this example to show you that every definition has its extremes. There is always one who acts a little bit weird, and this one is the weird filter. It's only X. And if you check the conditions, well, yes, X belongs to the family, the empty set not, assuming that our set is indeed non-empty. According to this definition, filters don't work on empty sets. If I have two members of F, well, it's both X. If I intersect them, I get X. Okay, and if I have a superset of X, then it's X itself, and it belongs to the family again. So this is really not much fun, but it does fall under the definition, and we have to account for that. Slightly less trivial. You can generate filters in a slightly less trivial way by taking a fixed subset of X, non-empty, and then take all the supersets of A. So every set that is a subset of a superset of A, a subset of X, but larger than A, that goes into the family. Again, checking that this works is not very difficult. We have a special case, of course. If you have a point in X, then you can take all the sets that contain the point. That is a filter. A bit more exciting. In topology, the neighborhoods of a point form a filter if you don't know what it is. Forget about it for the moment. If you do know what it is, then here is another example of a filter. Okay, now we get to the more exciting bit. If X is infinite, then there is an ideal on X that is pretty obvious. You take all the finite subsets of X. That forms an ideal. So if you go back to the previous page, and okay, for those who want to see it, is the empty set finite? Yes, it is. Is X finite? No, it is not. Is the union of two finite sets finite? Yes. Is a subset of a finite set finite? Yes. Done. It's an ideal. So in accordance to what I just said a few moments ago, we can create a filter from this by taking the complements of all the finite sets. Well, this is the cofinite filter, or the Fréchet filter on the set X. This one is somewhat different from the others. The ones that we have here, these are called principal filters. Principal in the sense that their intersection is non-empty. There is a point or a set in the middle that tells you what the members of the filter are. The Fréchet filter is not principal, it is free. If I take the intersection of the members of F, of the Fréchet filter, then I get the empty set. And that is what a free filter, a non-principal filter, is like. It runs away from all the points in the space. Let's see. Yeah, and the Fréchet filter is the one that we'll be talking about most of the time. You can generalize this, of course. If you have an uncountable set, say if you have, say, omega 1, that's the first uncountable set. You can take all the sets with countable complements. That is also a filter. You can take the reals, you can take the sets with countable complements. That's a filter. That doesn't quite fall under this definition, but you can easily modify this to get what you want. In general, if you have a cardinal kappa, this family is the Fréchet filter on that particular cardinal. Here is one. I'm not writing it down because we're going to be using it a lot, but for example, take all subsets of natural numbers Okay, the natural numbers include 0, so I have to do this. All the subsets of the natural numbers that if you take the harmonic series and you take the points in that subset and then the harmonic series converges, this is an ideal. Because if two series converge, then so does their sum or their union, so to speak. And so the complement the complements give you a filter. But just to be absolutely sure, so F there is one thing that needs to be emphasized, and I'll probably come back to this in a moment. When I said dual, and I had the relation between filters and ideals, keep in mind that when I have a filter, I look at the complements of the members of F, and conversely, when I start with an ideal, I take the complements of the members of I. What I don't do, and please remember that, I'm not taking the complement of F or the complement of I when I take the dual thing. Here is an example where you can actually check that if you take the if you take the family of sets for which the harmonic series diverges, that thing is definitely not a filter. And I give you two sets in that family whose intersection is empty, the even numbers and the odd numbers. The prime numbers and the non-prime numbers both have both belong to that family, but their intersection does not. So please, you can make this mistake once, but after that, no more. How do we create filters? That's the point of the point of the next, say, result theorem, if you will. And actually, this is going to be used in the homework that I will put on the website later today. I haven't put any homework on the website yet because I'm not 100% sure where I will end up today, but generating filters is something that will be used in the homework. Suppose Well, if you know what this is, then you know what I'm talking about. If you don't, I'm going to define this in a moment. But the finite intersection property, the definition of that is if this is the definition of the finite intersection property, the FIP. If you take finitely many members from G, then the intersection is non-empty. You may have seen this when you talk in some topology class where the talk was about compactness. Compactness can be characterized as if you have a family of closed sets with the finite intersection property, then the full intersection is non-empty as well. So if that sounds familiar, then you know what the FIP is. But if you have a family with the finite intersection property, then there is a filter okay, and here is my first misprint, but unfortunately I can erase this. There is a filter that contains G, and you almost can see where F is coming from. Of course, G must be a subfamily of F, but that means that all these intersections will have to be members of G of F as well. So, excuse me, start with what should we call this? H. Start by collecting all the finite intersections from members of F. Definitely that should be in the filter that we are trying to create. And define because what are we lacking in the filter when we create the family H? The family H satisfies the second property of filters. If I have two members from H, then their intersection is in H as well, because one of them is the intersection of 10 members of G, the other of 20. So the intersection comes from 30 members of G, and there you have it. What we're lacking is X and all the supersets of members of H. Well, we simply stick them in, and automatically X will be here. X will be one of these B's. And now we are done. Check that this works. Actually, I just did. And also check F is the smallest filter that contains the family G. Take any filter that contains the family G, it should contain H by definition. And again, by definition, it should contain F, and there you have it. F is the smallest filter that does it. And we will say that the filter is generated by this family. Many filters can be constructed in this way. You find a clever way to come up with a family of, with a finite intersection property, and then there is a filter that you create from it. Okay. What other things can we say about filters, and that is useful to have? Well, let me just, lest I forget, there are one or two terms that I use so often that I forget to define them. If we have two filters, then it may happen that one is a subfamily of the other. And we say G is finer than F. It's simply larger, but for some reason we like the word finer better. Or if G is finer than F, then we could say that F is coarser than G. The coarser thing is not used very often, but the finer thing is used all the time. Something happens to it, you have a filter, you have something else, and usually you say, oh, there is a finer filter that does this. And that is what you then try to prove. For example, convergence in topological spaces has lots to do with filters being finer than other filters. Just go back to your topology class if you have seen that. But there are two things about filters that are useful to know and to use in all kinds of circumstances. The first, slightly less so than the other, if if you have a family of filters and you take the intersection of that family, then you get a filter. Really? Well, is X in the intersection? Yes, because it is in every member of F. If A and B are in the intersection of all the F's, then if I have two members of the intersection, then they are in every filter. And so their intersection is in every one of those filters. And there you have it. And so now you may ponder this last one yourself. This is used occasionally. The next thing is used all the time, also in the homework and also in potential group interaction problems. Okay, here is one that is useful, very useful, and I'm going to prove this in a moment. We just saw if you take an arbitrary family of filters, then the union, the intersection is a filter. If I take an arbitrary family of filters, then there is no hope that the union is a filter. For example, think about this for a moment. If you take two distinct points and you take the principal filters generated by those points, then the union of those two filters is no longer a filter. And where are the culprits? Well, the intersection of x and of the singleton x and the singleton y is empty, and that destroys the filterness. So we cannot expect arbitrary filters to union up to filters, but if you have a chain, so ordered by inclusion, then you do get a filter. So let's check this carefully. Is the empty set not in the union? Yes, because it's not in any one of the members of F. So that's okay. Okay. This is something that I tend to forget all the time. All my sets are usually non-empty. And of course here, if I want to show that X is in the union of the family, there has to be something in the family, otherwise X is not there. But since the family is non-empty, there is at least one filter in it and X is in that filter, done. Okay, next step. Suppose A and B belong to the union. Well, A belongs to F1, B belongs to F2. We have two filters in the family F. A sits in one of them, B sits potentially in another one. But here we are lucky. Here is where we use that the family is ordered linearly under inclusion. F1 is a subfilter of F2, or F2 is a subfilter of F1. Let's say we are in this case. Then here, A and B both belong to F2. So the intersection of A and B is in F2, and therefore it's in the union. Here really is where it is necessary, needed, that the filters are comparable. The third one is, again, easy. If A belongs to the union, well, it is in one of the filters, and then B is already in that filter if B is a superset of A. So it's not even, you don't even have to say the union generates a filter. No, the union is a filter. Okay. And now we have set things up to get to our ultra filters. Let's call the filter U. Okay, we can define ultrafilters in many ways, and if you look back at the quote of Comfort on the first page, you saw something about a truth definition. Well, I'll come back to that in a moment, but I'm focusing more on the ultra, and the ultra sounds like it's really big or something like that, and this is what we take as our definition. If it is maximal in the conjuries of filters, and I know what you're thinking, what the hell is that? Of filters ordered by the subset relation. I'll come back to what it means in a moment, but okay. I found this once in the dictionary, and I use it when I'm running out of words, synonyms for sets. Sets, families, collections, conjuries, they are really big families. Don't take this too seriously. I could have said the collection or whatever. But the point is, filters are ordered partially, and we know what maximal and minimal elements are. So a filter is an ultrafilter if it's maximal, and I'm just writing down what the definition of maximal is. A filter, of course, this is what it means to be a maximal element with respect to a partial order. Nothing is bigger. If something seems bigger, it's equal to the point already. This is our definition of an ultrafilter. There is no strictly finer filter. how are we doing for time? Now, okay, so I define ultrafilters, fine. Why would I do that? Well, because I have a use for them. Are there any? It's one thing to define ultrafilters, it's another thing to actually show that there are ultrafilters. Yes. Those principal filters that I talked about a few moments ago, they're ultra. Why is that? Well, I could use, this is a moment where I could really use the characterizations that I'm going to talk about in a moment. But suppose for a moment that we have a filter finer than f of x. Okay, let A and G. Well, because well, singleton x belongs to G, it belongs to f of x. And so suppose we have a finer filter than f of x. Oh, wait a minute, it's equal to f of x. Every member of G is also a member of f of x. And this shows us that f of x is maximal. Okay, any others? So if are there any other filters? Is there a free ultrafilter? The answer is yes. Of course, if you want to prove that there are any, you should do so. And now, if you have been paying attention, you're going to see that there is something strange going on. Ulam and Tarski, two Polish mathematicians, proved in around 1930 that there are free ultrafilters on N. And what's the funny bit? Cartan's paper is from 1937. How could Ulam and Tarski prove that there were free ultrafilters when they hadn't been defined yet? I'll get back to that in a moment. Fortunately, Cartan himself every filter can be extended to an ultrafilter. And really, every filter can be extended to an ultrafilter. That's literally what Cartan stated in his theorem. No matter what the set, no matter what the filter, there is always a finer ultrafilter. And let me prove that. Not the way Cartan did, but the way most books do it these days. And the proof is actually, if you have been paying attention, it's just one line. You can say Zorn's lemma. Okay, let me flesh this out and then we'll have a short break and I can refresh my tea. The family let's call it phi. No, let's use that fancy new word that I just introduced. The congeries of all filters on X satisfies the conditions of Zorn's lemma, because the conditions, we need a partial order, and we need to know that every chain has an upper bound. Right? This is what Zorn's lemma wants us to check. You need a partial order in which every chain has an upper bound. If that is the case, then the partial order has many maximal elements. Well, what did we just prove a few pages ago? If we have a family of filters that is linearly ordered by inclusion, that is, if it is a chain, then the union is a filter. That filter is an upper bound for the chain F. We proved that just a few moments ago. So there are ultrafilters, and if F is given, apply this to you apply Zorn's lemma to this family because that still has the chain and upper bound property. So there, you give me a filter, I'll say apply Zorn's lemma to this, and there is your maximal filter. Okay, I will have a few comments to make about the necessity, or if you will, the usefulness of the axiom of choice in this thing, because this is blatant axiom of choice, of course. We say Zorn's lemma, or equivalently axiom of choice, or equivalently well-ordering theorem. a little bit of that is needed, and I'll comment on that in a moment. Okay, before the break, I just want to finish one thing and then we'll go to the characterizations. What did Ulam and Tarski do? Because they didn't literally construct ultrafilters. What they did both construct they constructed a function from the power set of n to 0, 1 that satisfies these three conditions. Okay, I'll use the word, the mu strongly suggests this. It's a measure. The measure of every singleton is 0. The measure of the whole set is 1. And of course, if you take disjoint sets, then the measures add up. But the measures only take the values 0 and 1. So, for example, if A and B are disjoint, then, well, both can have measure 0, and then 0 plus 0 is equal to 0. But if one of them has measure 1, then the other doesn't, because otherwise this wouldn't add up. What you can check, and this is really something that you should check on a piece of paper or whatever. So if you're really bored in the break, you can check this. And conversely, actually don't check this during the break, because you need the characterizations of ultrafilters that I'm going to talk about in a moment. Okay, let me try and pause the recording. And then in about 10 minutes or so, we'll continue. Yes, there he goes. Okay, so I gave you the sort of connection between something that looks like a measure and something that looks like an ultrafilter. You can prove this using the definition of an ultrafilter, but it's easier using the characterizations that I will talk about now. So what are those characterizations? Let me see, where are we? 6. So this is going to be page 7. And very often I abbreviate ultrafilter by UF because that's easier to write. So we have three characterizations of an ultrafilter. The last two are all quite similar. And the first one, number 2 here, really has the ultraness in it. If A satisfies so if you have a subset of X that intersects every member of the ultrafilter, then it actually belongs to the ultrafilter. That's one, even though it's number 2. The next one is this. If you have two members, if you have two subsets of X and their union belongs to U, then either one of them has to belong to U. And number 4 is actually a special case of number 3. So there is at least one implication that we have proven. So these 4 statements about a filter are equivalent. And so how do we prove this? Well, I just said we're going to prove the whole chain of implications. If I have a subset of X, then the union of it with its complement is everything, and that belongs to the ultrafilter. So there. 2 to 3. Well, so we assume that if we have a set that intersects every member of the ultrafilter, of the filter, then it belongs to the filter. Okay. Okay, if we have a set whose, if you have two sets whose union belongs to U, then we know that for every member of U, the intersection with that union is non-empty. And we're going to so if you look at this first statement here, then we can easily deduce this. For every C in U, either C intersects A or C intersects B. And we get what we can do, and this is not always the case in arbitrary logical formulas, keep that in mind, we can, as it were, pull the, we can use the distributive, we can distribute the universal quantifier over the two things that we take the disjunction of. And that is not always the case. This is not automatic. We need to do some work. And of course, we say, suppose not. Take if we have suppose not, it means that this is not, this thing is not true. It means that there should be a C that doesn't have an intersection with A, and there should be another C that doesn't have an intersection with B. So we take if this is not going to happen, then there's going to be something in U that doesn't intersect A, and there's going to be something in U that doesn't intersect B. But now, so here is our contradiction. Okay, so we have two implications now. Let's go from 1 to 2. Okay. So how's that going to work? So we know that we have a maximal filter and we have an A that satisfies, it intersects every member of U. Well, look at this family. Look at this this family of sets. Family we call G. What can we say about G? Well, X belongs to G. Why? We can take B equal to X itself, and then we find that A is a subset of X, and there you have it. The empty set is not a member of G because A intersect B is never empty. If I take something in G and I take something bigger, then it is also in G. Simply look at the definition. This D is bigger than this C, so there. Well, if C and D are in G, then there is a B1 such that this happens, and there is a B2 such that this happens, and then A intersect B1 intersect B2 is a subset of the intersection of C and D. Oh, G is a filter. Okay, now I need more paper. And here it is. G is a filter, lovely. But there are two things going on with G. A is a member of G. Really? Yes. Take B equal X. If B is equal to X, then A intersect B is equal to A itself. So A meets this criterion. The other thing is G is a filter that is finer than U. Why is that? Well, the same thing. If I take a member of U, then it meets this criterion. If we let C equal B itself, then we can take, if C is a member of U, then we take for the B C itself, and we get what we want. Ah, U is ultra. U is an ultrafilter, so it's equal to G. Oh, wait a minute. A was in G, so A is in B, is in U. So we're almost there. We have 1 to 2, 2 to 3, 3 to 4, and so we should try and get from 4 to 1. Let's see if we can make that work. There's no A yet. Take a filter that is finer than U. By the way, I saw in the chat why finer. Well, a finer filter usually has smaller sets in them, as you can see from the construction a few moments ago. And this is what the finer refers to. It distinguishes more. Well, take an element of G. We need to show that it is in U. Well, our assumption about the filter is now that it has to contain A or it has to contain the complement of A. But well, one of two will happen. X minus U is in U, or A is in U, but X minus A in U leads to a contradiction. Okay, so there. And here, by the way, in this characterization, this number 4 here, this is what Comfort referred to as this truth assignment. The ultrafilter decides for every subset of X whether it's true in the ultrafilter or false. Its complement is in the ultrafilter. And so you get a coherent assignment of truth for the subsets of X. In the homework, you will be asked to prove Pospíšil's theorem. So if you want to know how many ultrafilters are there, well, very, very many. Another thing that I want to mention, and it's actually going to happen right now, for later and for inspiration, and also to mention a few things that show you how things depend on the axiom of choice. Ultrafilters on omega. It's an old, this is going to sound really weird. I forgot to look up the year, but I think it was even before Ulam and Tarski. So the space-time continuum is in trouble here. If you have an ultrafilter, a free ultrafilter on the natural numbers, then you can construct a non-measurable subset of the reals, non-Lebesgue measurable. Of course, since we are assuming the axiom of choice, there is a non-measurable set. But if you want to know, say, how certain implications work, without assuming the axiom of choice, you can show this. So if you don't assume the axiom of choice, you can still prove this. And this tells you that you need some choice to get an ultrafilter, because there are models of set theory where every set of reals is measurable. In that model, there are no ultrafilters, and well, that's a pity. But how did Sierpinski prove this? He said, well, if there is a function such as the one that Ulam and Tarski constructed, then I can make a non-measurable set. And I think that was before Ulam and Tarski actually constructed those functions. I'm going to talk about special ultrafilters on omega for inspiration and more than anything else. We call an ultrafilter selective or a Ramsey ultrafilter if what? An ultrafilter is selective. Well, the name almost suggests the definition. If what happens if you take a partition of omega, then the ultrafilter picks one of the members of the partition. And if it's not able to do that, it's going to be very selective and have a set that is almost disjoint from everybody. It meets every set in at most one element. We will come back to this notion of selective and Ramsey filter when we do combinatorial set theory. And also when we start to talk about measurable cardinals, then this selectivity property will come back. Well, to haunt us is too strong a word, but we will be considering this idea later on. Equivalent. For every equivalent, and there's no, you don't really need to think very deeply, of course, for that. If you have a function from omega to omega, it induces a partition, and the selective set does exactly what you want. The thing is constant or injective on that member. Okay. Do these ultrafilters exist? Well, fixed ultrafilters are selective, but that's really not what we want. So I think I'll adapt the definition and throw out the trivial cases. Because if you have a fixed ultrafilter, it's fixed on one point, and that one point set does what we want here all the time. And actually, you always get the first alternative because you simply look which element of the partition your point is in. Okay. Do these ultrafilters exist? Well, the continuum hypothesis says yes. There are models. And there are models without Ramsey ultrafilters. Those are, if you ever encounter forcing and think back to this moment, the random real model has no Ramsey ultrafilters. Okay, now everybody tonight is going to Google the random real model and see what the hell that is all about. Fine. I want to sketch the proof that CH gives a selective ultrafilter, if only to show you that you can construct ultrafilters by recursion using the well-ordering theorem as well. And it generally goes something like this. So here is the construction from you enumerate using the ordinal omega 1, the set of all the functions from omega to omega. And this is where you use the continuum hypothesis. I should have put here the cardinality of the reals, but since I assume the continuum hypothesis, LF1 is the cardinality of the reals, so I can take an omega 1 sequence that contains all the functions. Next, I built a sequence of sets, of infinite sets, recursively. Okay, the first thing is easy. I start with omega. The next step is also easy. Remember, all the sets are going to be infinite. So X alpha is infinite. Take take an infinite subset of X alpha, on which F alpha is constant or 1-to-1. Is that possible? Yes, well, if F happens to be constant on an infinite subset of X alpha, take it. If not, it means that every set on which it is constant is finite, and then you have infinitely many sets because X alpha is infinite, and you pick one point from each of those infinitely many finite sets, and that's it. So think about it. I just said how you do it, and think about it later for a moment and write it down for yourself. Because the really new bit is what to do at limits. Where the hell does X alpha come from? Because, well, there's nothing that can help us to build X alpha. It could happen that the X betas have an empty intersection, so we cannot just take their intersection. So what do we do? Well, here is something that is happening lots of times in the infinite combinatorics of the natural numbers. Let's see, where are we? Here we use that alpha is countable. And we really, really use that alpha is countable. This is where the continuum hypothesis comes in all the time when you talk about ultrafilters on the natural numbers. The continuum hypothesis helps you, makes it way easier to construct things. And the reason is you need to do omega-1 many things, and halfway you only have to take care of countably many stuff. And that is what makes life much easier, believe me. And what I didn't say, but which will follow from the construction, so I'll come back to that in a moment, the family X beta, it has the FIP. And I will show you in a moment why that is true. Certainly, at the successive step, I cannot destroy the finite intersection property because X alpha is going to be an infinite subset of, well, I will show you in a moment why you cannot destroy the finite intersection property, because the sequence is going to have a stronger property than just that. But for now, we assume that it has the finite intersection property. And what are we going to do? We make a new sequence. We make a new sequence of sets. What do? We take the intersection of the first finitely many X beta I and throw away the first n natural numbers because we want the ANs to become decreasing and they get smaller eventually, and their full intersection is empty, of course. And what do? We take x0 to be the minimum of a0, and xn+1 is going to be the minimum of an+1 minus all the xi's we had so far. Assuming that the x beta i's have the finite intersection property, and even more so, and I really have to make that work in a moment, the strong finite intersection property, every finite intersection is infinite. Let's look at X. look at all the points that we have chosen so far. Then if we take the complement of x, the complement of an with respect to x, what are the points in x that do not sit inside an? There's only this many of them. The ans form a decreasing sequence of points. So x2 is here, x3 is here, so x3 is also in A2. x4 is also in A2, and so on. And so certainly, the complement of the difference x minus x beta n, that's a subset of x minus an, that is finite. We abbreviate this as x is almost a subset of x beta n. Almost meaning finitely many exceptions. So x is basically a subset of x beta n, except for finitely many straggling points. We let x alpha be just our x. What did we get when we go back to our construction? We will find that x0 is a superset of x1, is a superset of x2, is a superset of xn, is a superset of, and then here, what do we get at step omega? Well, at step omega, we get that x omega is almost a subset of x0, of x1, x2, xn, and so on. Right? At every successive step, we take a proper subset. At every limit step, we take a set that is a subset of everyone, except everywhere for finitely many points. Now, if you look closely, it shows you that if you take finitely many of these sets, then the intersection is infinite. And if you keep going, what you'll find is that later sets are always almost subsets of earlier sets. And this gives you the strong FIP it gives you that the intersection is always infinite. And this completes that construction. Like I said, the selective ultrafilters will be back when we talk about measurable cardinals. Okay, what's next? Well, we need to talk about completeness because we were talking about filters, and we just saw that maybe infinite intersections of members of a filter are empty, but we can always demand, and here we go again. We take a filter on a set and we take a cardinal. If what? If for every subfamily okay, the intersection of the subfamily is in F. Okay, this is only useful for regular cardinals. Think about this maybe for a while, and think about the fact that a singular cardinal can be chopped into fewer than kappa many pieces, all smaller than kappa. Kappa complete implies kappa plus complete. So there's not much interest in having singular cardinals in this definition. Are there any examples? Well, yes. If you have a regular cardinal, then this filter is kappa complete, simply because the union of fewer than kappa many sets of cardinality less than kappa is still of cardinality less than kappa. It's basically reformulating regularity. There are filters that are really complete, but those are the fixed filters. If you have an fx is an ultrafilter, no matter what subfamily you take, the intersection is in the filter because it contains the point x. So that is not really exciting. Sigma complete. That's the same as aleph 1 complete. So it means that if you have a countable subfamily, then the intersection is still in the filter. And now, of course, we get a serious question. Are there any sigma complete ultrafilters? Well, definitely not on omega. And of course, free ultrafilters. Don't forget about the fixed ultrafilters, free ultrafilters. Definitely not on omega, because if I take a free ultrafilter, then all these sets are in there and the intersection is empty. Also not on R. That's easy, relatively easy to prove, and I put that in the homework. mainly because the argument is so nice and it's nice to figure it out for yourselves. Anywhere, you might ask. Well, this leads to very large cardinals. That's why there's two E's in the very. Measurable cardinals, they're called. Why? Well, the point is that the, okay, real measurable has some other meanings, but it would be a proper real measure because a measure in measure theory is a sigma additive function that does all the things that we saw a few moments ago. And that's where the term, basically where the term measurable cardinal comes from. There is a function 0, 1 valued that acts like a measure. Okay, this is a good moment to have a short break again. So we'll reconvene in about 10 minutes because I haven't shown you very many kappa complete filters, and the rest of the afternoon we'll be talking about a very nice kappa complete filter on regular cardinals. And so now I have to find the recording bit. There we go. Like I said, we haven't seen any interesting examples other than sets with small complements of interesting complete filters yet. And a very nice kappa complete filter we'll be talking about today, and things that go with them. For the rest of today, kappa is regular, uncountable. This doesn't really work very nicely for singular cardinals. Actually, you can make it work, but then you simply reduce it to its cofinality. So again, you go to a regular cardinal. C, subset of kappa, is closed and don't ask me why the abbreviation came out this way, but this is how most everybody abbreviates closed and unbounded, cub. If what? Well, if it is unbounded, and that just means cofinal. So that is not really a new term. We have talked about, we've been talking about cofinal sets a lot in defining the cofinality, for example, and it is closed If you're like me and you grew up with ordered topological spaces, then closed, when I say closed in the order topology, is that's it. But ordered theoretically and for our purposes, this is the definition of closed. Every limit point of C is in C. And what does that mean? That means that if alpha is equal to the supremum of C intersect alpha, then alpha is in C. So let me draw a picture. Here is kappa. Okay, not very exciting, but this is what an ordinal looks like anyway. And okay, so the red points are something like C. It doesn't do it justice, but I have to do something. And suppose we have an alpha less than kappa, and it so happens that if I take the points of C below kappa and the supremum of that is alpha, then alpha is deemed a limit point of C. And we want a set to be closed if it contains all of its limit points. This is actually a topological definition. This defines closed in the order topology of kappa. So I could take this as an exercise, or you can take this as an exercise. I can give it as an exercise. If you work in a topological space and you have a family of closed sets, then the intersection of that family of closed sets is again closed, arbitrary, and the same goes here. However, for the closed unbounded sets, more is true, way more, as we shall see in a moment. Here is the first bit. If I have two closed unbounded sets, then their intersection is closed unbounded. Okay, closed, we believe that. Unbounded, really? Can you have two, if you take two closed sets that are unbounded, must their intersection be unbounded as well? Can they not diverge close to kappa? No, and that is where the uncountableness and the uncountability and the regularity come in. Take alpha arbitrary. And we do the following. So we're going to prove that the intersection is unbounded, that it is closed. I leave to you to think about. I may give a hint later on. But unbounded is always the sticky point. Closed is not really. So here we go. We have our alpha. Well, C is closed unbounded. So there is something above alpha that is in C. D is closed unbounded. There is something in D that is above alpha 0. And we can always take the minimum thing that is bigger than whatever we have. So we don't even have to invoke the axiom of choice here. We can always take minimum, 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 because we have well orders already. Well, you can see where this is going. We construct recursively an increasing sequence of ordinals where the even ones are in C and the odd ones are in D. And let beta be the supremum of that, because kappa is uncountable regular. Beta is less than kappa. And beta is also the supremum of the even numbered alphas, so beta is in C. Beta is a limit point of C because it's the supremum of a subset of C even. It is also the supremum of the odd numbered alphas. So again, it is in D. The intersection of two closed unbounded sets is closed unbounded. But I promised you a kappa complete filter, and that is what we're going to do now. I could have done the proof of kappa completeness all at once, but I want to give you the idea to see what you have to do to show that the intersection of a small family, smaller than kappa, of closed unbounded sets is closed unbounded. And so what do we do? Well, we have a small, where are we? We have a small family of closed unbounded sets. Well, here we go. Shouldn't forget to go back. Yep. So we take a sequence of closed unbounded sets, and of course we take fewer than kappa many. So here is the gamma is less than kappa. And here is what we're going to do. Take the ordinal, what did I call it? I didn't call it anything. Take the ordinal gamma times omega. That means omega copies of gamma. That's the ordinal that we're taking. And what do? We make given alpha in kappa a sequence. Okay. We're going to make a sequence of points that looks like this. Delta eta, and eta is less than that ordinal that we just took. And how do we construct this? Well, look at this gamma, those copies of gamma here. Okay, we start with beta, and we take delta 0 in C0. Delta 1 in C1. Delta, what shall we say? Oh, delta alpha in C alpha. And we keep going. And then we get to gamma. For every alpha less than gamma, we do this. We can keep on doing this because our sequence is never cofinal in kappa, because kappa is regular, uncountable, and bigger than gamma. So whenever I meet a limit here, I can always go a bit up and still stay below kappa and find something in the closed unbounded set C alpha. Okay, but then we do the same thing again. We start at gamma. We take something above everything in this sequence, still possible because of regularity. And we take delta gamma in C0 again. And delta gamma plus 1 in C1. And delta gamma plus alpha in C alpha. Okay, now you can see where this is going. We go through the whole set of natural numbers, and every time we go through a whole gamma sequence of our gamma sequence of closed and bounded sets, and we keep picking points in those closed and bounded sets. It's always possible because of the regularity of kappa. And when we're done, we take delta to be the supremum of all those delta etas less than gamma times omega. Delta is still less than kappa because we are working in this regular cardinal kappa. But delta is also the supremum It's also the supremum of the delta gamma times n's. Why? Because when I look at this column, so to speak, in the matrix, it is cofinal in this sequence. This sequence has cofinality omega, and these ordinals here are cofinal in it. These ordinals are also cofinal in it. And this goes for every alpha. Every one of those, say, columns in the matrix is cofinal in the sequence. And that means that delta is the supremum of all of those things. And there we have it. And again, the intersection is closed because basically so to show why it's closed, you have to consider this. If delta is the supremum of delta intersect, then certainly delta is the supremum of delta intersect C alpha for every alpha. So that proves closed. That's not the point. The point in proving closed unbounded is in the unbounded. So we started with a beta, we found a delta that was quite bigger, and it is in the intersection of our C alphas. The intersection is closed unbounded. Okay, now because of what I said, the C kappa, it's going to be all the A's in kappa with there is I mean, the closed unbounded sets have the finite intersection property, even way more than that. So they generate a filter, and that is the filter that we're talking about. And what we have just seen is that C kappa is a kappa complete filter. Why do we talk about the closed unbounded sets anyway? Well, they occur, and that's what you will see in the group interaction. In model theory, the elementary even, so if you have done your model theory, you know what I'm talking about. If not, you may encounter this in a logic course, but for those who know or will do the model theory, here is something, here's a place where they are if you take, for example, if you were to have a model of size Aleph1, then, oh, I should mention here, of smaller cardinality. So if you have a model of some theory and you take all the submodels that are, say, countable, or, well, if your model has size Aleph1, you look at the countable submodels. If it's size Aleph2, you look at the countable and the ones of size Aleph1. They form a closed unbounded subset of the full. They form a closed unbounded subset of the domain of that model, which you will order in type its cardinality. And that means that, and there is lots of stuff you can do with that. Reflection things, look up reflection, look up the Lowenheim-Skolem theorem. All these things work together to get all kinds of interesting stuff in model theory, interesting applications, and whatnot. And in the group interaction, there is a small sample of what you can meet here. If you have a group, say, on Aleph1, on omega 1, then there is a closed unbounded set of countable subgroups. Many countable subgroups you will find in omega 1. So, where are we? Yeah. There is more. What more is there? Well, the cup filter has one extra property that you don't see very often, but it's really important in combinatorial set theory and all kinds of applications thereof, and I'll mention that in a moment. Okay. If you take a kappa sequence of closed unbounded sets, chances are that the intersection is empty. For example, if you take the final segments, those are closed and unbounded sets, their intersection is empty. So that is not very exciting. But there is another thing you can do to the closed unbounded sets, and that is take this. You take the deltas with the following property. For every alpha less than delta, delta is at least in the set C alpha. This is called diagonal intersection. So you don't really want points that are in all the intersection, but you look at the sequence and you say, I am delta. I'm looking at the C alphas where alpha is less than delta. I would like to be in that intersection, please. And the deltas for which this wish is granted is those form the diagonal intersection of the family. And the theorem is this intersection is closed and bounded again. And I put here an exclamation mark because this is really important in many applications of closed and bounded sets and what I hope to talk about in a moment, stationary sets. And here it goes. Why is it closed? Well, suppose you have delta is the supremum of delta intersect that diagonal intersection. We want to show that delta is actually in that thing as well. So take a gamma less than delta, take, okay, I forgot this. I always have to do this the right way. It's closed. Okay, I have my letters mixed up, but never mind. If you take a gamma less than delta, well, there are many betas between gamma and delta that are in the diagonal intersection, and that beta is in the intersection of all the C alphas for alpha less than beta. So it's in particular, it's in C gamma. So if beta sits between gamma and delta and beta is in the diagonal intersection, then beta is in C gamma. Oh. it implies that delta is in C gamma. And gamma was arbitrary, so there, delta is in the diagonal intersection. Unbounded, well, take beta less than kappa, take we know that the intersection of all the C alphas where alpha is less or equal to beta is closed unbounded. So we take a delta bigger than beta in that set. The intersection of all those C alphas for alpha less or equal than delta 0 is closed unbounded. So we can take something in it. And you can see where this is going. This doesn't stop. And in the end, the supremum of that sequence is in the intersection. Why is that? Well, take an alpha less than delta. Alpha is less than one of those delta n's. And then that sequence of delta i's where I starts at n, that sits inside C alpha, and so there. Okay, now I have about 5 minutes to talk about the main topic, basically. I'll skip a few things, but to get straight to the thing I want to do. C kappa is not an ultrafilter. There is a proof of that in the homework for omega 1. There is a proof for the general case in Jech's book. I will not be talking about that because it would take us too far afield. You can you can split kappa into kappa many stationary sets. And what does stationary mean? S is stationary if it intersects every closed unbounded set. That is what we call stationary. Now, the definition of the word stationary, so they say the word stationary actually comes from a property of stationary sets. And so why don't I finish with that important theorem? And maybe next time I'll talk a little bit about some other things that show you that the club filter is not an ultrafilter, but here, okay, no, I'll do that at the end. the pressing down lemma. If S in kappa is stationary, and okay, suppose that S doesn't contain 0, or if it contains 0, we forget about this. Then F is constant on a stationary set. This is what makes the stationary sets and the closed unbounded sets so important. There is a homework exercise that applies this, but there are tons of applications of this theorem. So this is one that you really need to know in your set theoretic career, so to speak. The proof is actually not very difficult given what we have just proven. If not, and yes, we do this by contradiction, then if it's not constant on a stationary set, that means that every set on which it is constant is not stationary. But if you are not stationary, then you find this. If not, if the set on which you are constant is never stationary, that means that for an alpha, the set of betas on which you get value alpha is not stationary. That means there is a closed unbounded set disjoint from it. Well, we have a sequence of closed unbounded sets. We get, this is blatant axiom of choice. We choose C alphas simultaneously and whatnot, but okay, we're axiom of choice believers. We get a sequence of closed unbounded sets. Look at the diagonal intersection. So it's constant on a stationary set. Suppose not. Then for every alpha, we get a closed unbounded set and everything. Take the diagonal intersection of that, and what do we get? Well, D intersect S is non-empty. Because S was stationary, it intersects every closed unbounded set. In particular, this diagonal intersection. Take an alpha. Now, F alpha is less than alpha. So alpha belongs to C of F alpha. It's in the diagonal intersection. It means it's in the intersection of all the C betas where beta is less than alpha. Okay, so F alpha is not equal to F alpha. I should have turned these around, but never mind. If beta is in C alpha, then F beta is not alpha. Now, replace beta by alpha and alpha by F of alpha. And here we get our contradiction. And to finish, and it take a last minute, one thing. Here is a quote from a paper by a French mathematician, Bloch. Here is where you find the definition of the term stationary. And the term stationary actually means, basically, it satisfies this pressing down lemma. It is constant on every regressive function is constant on a large set. But the thing that I want to finish with, because it's useful in the homework, is this. If you have a family of subsets of kappa, and the family is small, such that the union is stationary, and then some S alpha is stationary. Actually, the contrapositive is better. The non-stationary sets form the ideal that is dual to C kappa. And since C kappa is kappa complete, so is the dual ideal. If you take fewer than kappa many non-stationary sets, then the union is still non-stationary. Okay, this is what I had planned, and this is what I did. And it only took me 3 more minutes than necessary. And I had, sorry about those 3 minutes, but okay, I'll stop the recording and finish